So we're going to look at, start looking at gases laws, starting with Avogadro. Before we can talk about gas laws, though, we need to talk about volume. So the SI unit, or the metric unit for volume, is meters cubed. That is used on the industrial or engineering scale, so it's way too big for us. So we tend to use centimeters cubed or decimeters cubed, and you have to be able to convert between them. Now, I know you remember King Henry died unusually drinking chocolate milk. So if we're going from centimeters to decimeters, we would go one direction. But because we are cubing these values, you want to move 3 places each time. So if we said we had 15 centimeters cubed and we want it to be in decimeters cubed, we would move the decimal to the left because C to D is to the left, but we would want to do it 3 times because it is cubed. So we would say that it is 0.015 decimeters cubed. The other thing to remember is that centimeters cubed is the same thing as a milliliter, and so decimeters cubed is the same thing as a liter. But for IB, we don't use liter and milliliter, we use centimeters cubed and decimeters cubed. Sometimes it might be easier to think in terms of milliliters converting to liters than centimeters cubed converting to decimeters cubed. But you should only be using centimeters cubed and decimeters cubed. So Avogadro's law relates the gas volumes to moles. Gas volume is determined by N, which is the number of moles, temperature, and pressure. There are equal volume of gases when measured at the same temperature and pressure that contain equal moles. So volume and moles are directly related. So all gases under the same conditions have the same molar volume. And at STP, it is 22.7 decimeters cubed. So 1 mole is 22.7 decimeters cubed at 273 Kelvin and 100 kilopascal. So because we're defining pressure in terms of kilopascal instead of ATM, that's why it's 22.7 as opposed to 22.4. But this value is given to you in your data booklet in section 2. So if we look at a couple of examples and what this would mean for us, we have our reaction. We're given 40 centimeters cubed of each of our reactants. So we know that this is a limiting reactant problem because we have values for more than one reactant, and we're trying to figure out the volume of carbon dioxide that is produced. So the first thing we need to do is figure out the limiting reactant. Now, because all volumes are measured at the same temperature and pressure, that would mean they can be treated as if they were moles. In other words, if we were to convert these 2 moles, we would have to divide them both by 22.7, which mathematically would not differ or not change the outcome. So if we pretend that the centimeters cubed is moles, then we know that the CO is going to be the limiting reactant because we need twice the amount that we have of O2, and we don't have twice the amount. So CO is our limiting reactant, so we're going to use that to determine the volume of carbon dioxide. If we're starting with 40 centimeters cubed of CO, again, there's equal moles because they're at the same temperature and pressure. So we can set up a mole ratio using our volume and the coefficients. So 2 carbon dioxide, 2 carbon monoxide. So that would mean I would get 40 centimeters cubed of carbon dioxide. All right, looking at another problem. Pure oxygen gas was first prepared by heating mercury to oxide. What volume of oxygen at STP is released when heating 12.45 grams of the mercury to oxide? So we have 12.45 grams of HGO, and we are looking for the volume of oxygen. So we're going to, at STP, so that tells me that 1 mole is equal to 22.7 decimeters cubed. So we're going to use, because it says at STP, we're going to use that conversion factor. So we're going to start with 12.45 grams of HGO. And the first thing that we want to do is convert that to moles. So we would pull the unit and the substance to the bottom, and then mole of HGO on the top. 1 mole, and then we look at the periodic table and we find the molar mass. 216.59. So our grams would cancel when we divide. We're at moles of HGO, but we want oxygen, so we're going to set up our mole ratio. Remember, it's only during a mole ratio that we can change the substance. 2 is the coefficient in front of HGO. 1 is the coefficient in front of the oxygen. So when we multiply and divide, the moles of HGO would cancel, leaving us with moles of oxygen. But we want the volume of oxygen, so we're going to go one more time. Since it's at STP, we know 1 mole is 22.7 decimeters cubed. So then when we divide, the moles of oxygen would cancel, and then we can multiply and divide our way across. For significant figures, it's based on the given, and since the given has 4 significant figures, we want our answer to have 4. So it would be 0.6524 decimeters cubed of oxygen. Now, if the question asks for the answer to be in centimeters cubed, we would have to do a conversion. So King Henry died unusually drinking chocolate milk. To go from decimeters to centimeters, we would move the decimal 1 place to the right. However, it is cubed, so we're going to do that process 3 times. And so there would be 652.4 centimeters cubed of oxygen. You only have to do that part if the question specifies centimeters cubed. All right, don't forget to fill out the Google form and try the problems from the text.